So in today's lecture, we will look at the design of battened column. Battened column is a composite column, and if you remember during our modeling lecture, what we did was we designed our columns in section designer property or section designer in ETABS in this way. We suppose that there were two medium channel sections and these were placed toe to toe or front to front, whatever you want to call, and these columns were joined by batten plates in these two sides. So you may also place these channel sections back to back in this way, and then again join these channel sections by using batten plates on these two sides here. So we adopted this approach in our ETABS modeling. Now if you go to your ETABS model and go to define section properties frame section, here we have these two ISMC 300 modify show property and section designer. You can see that if we have drawn these two batten plates in our section designer, then what the software does is it assigns these batten plates along the whole length of the column. Whereas in real life, if this is the face of the column, then these batten plates are just spaced at a certain distance apart. So if here is one batten plate here, and there is another batten plate here, and there is another batten plate here. So these batten plates is not constructed along this whole length of the column, but rather they are placed at certain specified intervals. So while designing in section designer, you may draw these or you may not draw these batten plates. So in case where you haven't drawn these batten plates here, but have drawn only these two channel sections, then when designing your steel frame, then these columns may fail because this only two channel section may not be sufficient to bear all the loads coming onto those columns. Whereas if you have drawn these batten plates, then the software may show that these columns are oversafe. So what we will do is we will look at the load, axial load coming onto our columns, and then we will design this battened column manually. So that is what we are going to look at today's lecture. So let me just cancel this here. So here is an Excel sheet for the design of battened column, and I will go through the steps one by one, and then you may even prepare your own Excel sheet. Just open any book related with the limit state design of steel structures. Follow all the steps given in worked out examples by simultaneously looking at the codal provisions, and then you may even prepare this Excel sheet by yourself. So for the design of battened column, you have to go to section 7.7 in our IS 800 code. The 7.7 section, there are various provisions relating with the design of battened column, and these codal provisions must be strictly followed. So wherever any calculation in our Excel sheet is according to any codal provision, then I will refer to that codal clause simultaneously while discussing the steps here also. So first, let's see here. First, there are some data to be filled here. So this, if your cell is given this blue color, then you have to just fill this data by yourself, and the values in green color, these are generated by using some formula. So first you have to find the factored axial load acting on your column. For that, we have already performed analysis and design here. Let's go to display and show tables. We want to see the member forces in our compression members, that means our columns. So go to analysis result, element output and frame output. Currently I only want to see the frame forces for columns, so select these element forces columns and then click on OK. So if you see here, this column here, P represents the axial force that is coming onto our columns. So if I right click on this P here and then click on sort ascending, you can see that the maximum value of negative force coming onto our column is 313.7471. Similarly, if you go below, then you can see that the maximum positive value is 26.3225. So let me take this axial force 313.7471. I will write this as 313.75 here. So this is the factored axial load coming onto our columns. Let's see here. This maximum load is coming onto our column C7 at story 1. So let me select this column here. For that, what I will do is, let me close this, go to select by label, and then frame label. Let's select story 1 here, and then select column C7 and close. So if I do show selected objects only, here is our C7 column. So this is our C7 column. And if you right click on this column, and then you can see different design details here, and then left click on this details here, a details form will appear according to which this column has been designed. And in this detail column, if you look at this table here, table of basic factors, you can see that our K factor is 1.783 and our length is 2950 mm. So we need that here because we want to find the effective length of column here. So effective length of column is given by the product of the length of the column and the K value, and that effective length is already given here. This is 2.95 meter here. So let me write this 2.95 in our Excel sheet here. 2.95. Now the grade of bolt that we will be using is 4.6. This grade of bolt, you can see the details in IS 1367 part 3 code. So what does this 4.6 signify? Let's see here. The number before decimal indicates 1 by 100th of the nominal ultimate tensile strength. That means if you want to find the tensile strength of bolt, you have to take this digit before decimal, that means 4, and multiply it by 100. So 4 into 100 is 400 megapascal. This is the tensile strength of bolt. And the number after decimal indicates the ratio of yield stress to ultimate stress, expressed as percentage. That means after decimal it is 6 here. So if you multiply 0.6 into 400, you get 240, and this 240 will be the yield strength of bolt. So 4.6 grade of bolt means 4 into 100 tensile strength, and then 0.6 into 400, 240 is the yield strength. And let us suppose that the diameter of bolt is 20 mm, then the diameter of hole will be 22 mm. This you can see from your IS 800 code, the clearance that is required for any given diameter of a bolt. So for 20 mm, 20 plus 2 is 22 mm. And here we have the minimum tensile strength of steel 410 megapascal and minimum yield stress 250 megapascal. You can get these values from ETABS also. Just go to define material properties and select EFE 250, and then left click on modify show material, and then left click on modify show material property design data. You can see that our minimum yield stress is 250 megapascals and minimum tensile strength is 410 megapascals. So these same values we have used here, 410 and 250. Then gamma mb partial safety factor for bolts 1.25 and gamma m naught 1.1. You can get this from table 5 of IS 800. Now the first step in designing our batten column is to assume design compressive stress. Take these any values. Just suppose any value by yourself and you can use that value as design compressive stress. And later when we perform some calculation, then we will check for this design compressive stress. For now I am using 180 Newton per square millimeter. Now let's find the area required to resist the given factored load here. For example, we have the factored load 313.75 kilonewton, and the design compressive stress we have assumed is 180. So if you divide this factored axial load by design compressive stress, you will get the required area. So convert it into kilonewton and then divide, you will get the required area to be 1743 square millimeter. Just do this, 313.75 divided by 180. So this will be the area required. Now let us select any trial section first. We have assumed that our composite column or our built-up column is composed of two medium channel sections of depth 250. So here is given a list from which you can select the required channel section, and based on the property that you select here, the different properties or geometrical properties of your section will be changed here. So currently I will select ISMC 250. So now we are given some parameters of this 250 mm channel section. For example, the depth of section, sectional area, width of flange, moment of inertia about x-axis and y-y axis, radius of gyration about x-axis and y-y axis, and then cyy and g. If you look at this diagram on the right hand side, cyy is the distance given here. If this is the y-axis, then cyy is the distance from this edge to this y-y axis. So these are the geometrical properties of this ISMC 250 section. So for any built-up section, we always assume buckling class C. If you want to know in detail about buckling class, then go to table 10 of IS code. That is the same code IS 800, where it talks about the buckling class of cross sections. Now let us find the slenderness ratio of our built-up columns. IS code in this clause 7.7.1.4 says that the effective slenderness ratio of battened column should be taken as 1.1 times the maximum actual slenderness ratio of the column, and that is to account for shear deformation effects. So first we have to find the maximum slenderness ratio of the column, which is given by effective length over the radius of gyration REXX, and then multiply it by 1.10. So effective length we have here 2.95 meter, and REXX value is given here 9.94 cm or 99.4 mm. Divide the effective length by REXX and multiply it by 1.10, you get the slenderness ratio to be 32.64 mm. Now based on this slenderness ratio, you have to find the actual design compressive stress. At our very first step, we assumed a design compressive stress 180 Newton per square millimeters. But now we have to find the actual compressive stress. And that actual compressive stress is derived from table 9C of IS 800. So let me go to that code here. Okay, this is our table C here. At the very top, you can see that table 9C gives design compressive stress for column buckling class C. So we assumed, or we know that for composite columns or built-up columns, our buckling class will be C. So here we have the yield stress value along this horizontal axis. Our yield stress value is 250, and then we have here the slenderness ratio, which is between 30 and 40. So you have to interpolate the value of these design compressive stress for 250 mm or 250 megapascal yield stress between this 30 and 40. So for 30 we have 211, and for 40 we have 198. So for 40 we have 198, and for 30 we have 211. You have to interpolate between these 30 and 40 to get the slenderness ratio, to get the design compressive stress for slenderness ratio 32.64. So by interpolating, you get the value to be 207.57. That means this is also between 211 and 198. Now use this design compressive stress to find the design compressive strength. From stress to strength is given by the product of this design compressive stress into effective area. So if you go to this codal clause here 7.1.2, what it says is that the design compressive strength should always be greater than the P value or greater than the design compressive stress value. So we have assumed our design compressive stress to be 180 Newton per square millimeters. Now if you multiply this design compressive stress that we have got here 207.57 into effective area, this effective area is this same sectional area that we have obtained using this sectional properties 38.67 centimeter square. You get to be 1605.33 kilonewton. So this 160.5.33 kilonewton is very much greater than the actual load that is coming onto our column, that is 313.75 kilonewton. So the section that we have chosen is safe, or our strength is greater than the load coming onto our columns. To calculate this effective area, you can go to this 7.3.2 effective sectional area AE. What it says is that the gross sectional area shall be taken as the effective sectional area for all the compression members fabricated by welding, bolting and riveting, so long as the section is semi-compact or better. Holes not fitted with rivets, bolts or pins shall be deducted from gross area to calculate effective sectional area. So our effective area is equal to the gross sectional area. So we have taken this same gross area, that is 38.67 centimeter square here. Now after getting this design compressive strength greater than the actual compressive force coming onto our columns, we can say that the trial section that we have chosen for now is safe. Now after ascertaining the section that we are going to use, now we have to design for the batten plates. So for design of batten plates, as I already talked about earlier, just go to this clause 7.7, which talks about the design of battened columns in our IS 800 2007 code, and follow the steps there. First, we will find the spacing between the channel. Spacing here is represented by D. So this D means, if you look at our diagram here, from this edge to this edge here, this is the D here. So what we will get after finding this D is that we already know the width of the flange here. The width of the flange in case of our ISMC 250 channel is 80 mm. Similarly, this will also be 80 mm here. Now if you find D, you can find the spacing required between these two channels here. So to find D, use parallel axis theorem, use this formula that is given here. CYY value we already know. A is the cross-sectional area. IXX value is also given above. Now using this formula, we get the spacing to be 238.91 mm. Remember, this formula will be changed if you are using the channel sections back to back. That means in this way. So this is toe to toe or front to front, and this is back to back. So the formula will be changed when you are using these composite column sections back to back. For now, use this formula, and for back to back columns, just you can consult any book there. So using this formula, we get the spacing, minimum spacing to be 238.91 mm. We will take currently the spacing is 250 mm. So if you take this 250 mm, what will happen is that we have made a circular section here, because this will also be 250 and this will also be 250 here. And this spacing will be 250 minus 80 minus 80, which will come out to be 90 mm. So this clear spacing will be 90 mm here. Now after deciding the spacing between the channel sections, let us find the spacing between the battens. So 7.7.3 in our IS code says that the spacing of battens shall be such that the slenderness ratio of any component over that distance shall be neither greater than 50 nor greater than 0.7 times the slenderness ratio of the member as a whole about its ZZ axis. So for that, what we will do is first find this value 0.7 into lambda into RYY. This RYY is the radius of gyration and lambda is the slenderness ratio. This comes from this second condition here, nor greater than 0.7 times the slenderness ratio of the member as a whole about its ZZ axis. And in second, find the value of 50 into RYY. So this means not greater than 50. The slenderness ratio shall not be greater than 50. So find these two values, and then you have to choose the spacing in such a way that the spacing should be lesser than the lesser of these two values. For example, among these two values, the smaller value is 543.78 mm. So choose a spacing lesser than this value. For now, I will choose it at 500 mm. So this will be the spacing between your battens. That means this spacing is center to center of its end fastenings. So this will be the spacing between your battens. And now to find the actual size of the battens, what we will do is we will find the size of end battens and then we will find the size of intermediate battens. So for finding the size, you can look at this clause here 7.7.2.3. So first of all, let me see here. So this is for end battens. So when plates are used for battens, the end battens shall have an effective depth not less than the perpendicular distance between the centroids of the main members. That means so if this is our one channel section here and this is your another channel section, the centroid of this channel section passes somewhere at this distance. So this distance is CYY, and the centroid of this channel section passes here. So this distance will be CYY. So what the code condition says is that the end battens, that is the depth of the end battens or effective depth of the end battens, should not be less than the perpendicular distance between the centroid of the main members. So find here the effective depth of end battens using this formula D plus 2CYY. You get to be 296 mm. D means the spacing that we got here 250, and CYY value we have from here 23 mm. So twice into CYY plus D will be 296 mm and 2 times BF. So what it also says is that in no case shall the effective depth of any batten be less than twice the width of one member. So the width of our channel is 80 mm and twice the width means 80 into 2 is 160 mm. So we are using the effective depth as 296 mm here. So this 296 mm is greater than this, twice the width of that section. So it is okay. Now if you assume the pitch to be 35 mm, our total depth will be 296 mm plus 2 times 35 mm. Because if this is our batten plates here, then the effective depth means, suppose this is the center of one bolt that we have used here and this is the center of another bolt. So pitch for here will be this distance, which is 35 mm, and similarly pitch for here will be 35 mm. So the total depth of our batten will be the effective depth plus 2 times pitch. We have considered pitch as 35 mm, so our total depth of our batten will be 400 mm. So similarly, you can also determine the size of intermediate battens. First, find the effective depth of intermediate battens. What it says is that the effective depth of intermediate batten is given by 3 by 4 times of the effective depth of the end battens. So that means our end battens are always larger than the intermediate battens. So 3 by 4 into 296 is 222, and the total depth will be the same, 222 plus 2 times this pitch 35 mm, you get to be 292 mm. We take the total depth of our intermediate battens as 300 mm. And remember, what does depth mean here? You can see that here it says the longitudinal effective depth. That means if this is our column and these are our batten plates, this is the total depth of your battens along this longitudinal direction. So this is the width of your batten. This width of your batten will be kept equal to the value of D. That means this total spacing here, and the depth we just found out. So the depth of our end battens is 400 mm and the depth of our intermediate battens is 200 mm. And finally, two things left to be checked is the thickness of batten plate. What it says in the same code or same clause 7.7.2.3 is that the thickness of batten plate should not be less than 1/50th of the distance between the innermost connecting lines of rivet, bolt or weld. That means D by 50, the total length of your battens or the total spacing 250 by 50 is 5 mm. The thickness of your batten plate should not be less than 5 mm. We take the thickness to be 8 mm here. And finally, the length of your batten plate will be equal to your spacing. That means this D value. So the length of your batten plate is 250 mm. Finally, the end batten size is given by 250 into 400 into 8. 250 is the depth or length, 400 is the depth and 8 is the thickness, and intermediate batten is given by 250 into 300 into 8. So you can see that the end battens have a larger depth compared to the intermediate battens. So if you check for the forces acting on this intermediate batten and they are safe, then our end battens will obviously be safe since they are of a larger size and you do not need to check separately here. Now finally, to check for these battens, we have to consider three different forces. One is the transverse shear, one is the longitudinal shear, and another is the bending moment. This transverse shear is given in 7.7.2.1, which says that the transverse shear is taken to be equal to 2.5% of the total axial force on the whole compression member. So our axial force we have got at the very top here, 313.75. If you take its 2.5%, then the transverse shear comes out to be 40.13 kilonewton. Similarly, longitudinal shear is given in the same clause here, VTC by NS. VT is the transverse shear. C is the distance between center to center of battens longitudinally, which we got above or which we calculated above, if you remember from this spacing between battens C. And then N and S we have. N is the number of parallel planes of battens and S is the minimum transverse distance between the centroid of the bolt group connecting the batten to the main member. So S value you can calculate, you can see here, and then you can derive the value of VB, that is the longitudinal shear. You can see that the value of longitudinal shear is very large as compared to the transverse shear. And finally, bending moment value is given by VTC by 2N. We have all these values here, N, C, VT, and the bending moment comes out to be 5.02 kilonewton meter. Now we have the forces on our battens. Now we have to check its strength. And the thing that I talked about before is written here. If intermediate batten is safe, then the end batten will automatically be safe because size of end batten will be greater than that of intermediate batten. So for this check again, okay, I think I have not saved here. For this check again, this is given in your code itself. First, shear stress is calculated by this formula, VB by DI into T. VB means the longitudinal shear and DI is the, let's see here, what is DI? DI is the size of intermediate battens, that is the overall depth of our intermediate batten, and T is the thickness. So if you use this formula, the shear stress comes out to be 24.59 Newton per millimeter square. After finding this value, find this value Fy divided by root 3 into gamma MO, or this is the partial safety factor. That comes out to be 131.22. Now since this shear stress is lesser than this value here, our battens are safe in shear. Similarly, find the bending stress using this formula here, 6m divided by Ti into Di square. Di is the depth, Ti is the thickness, and m is the moment value that we got here, 41.81. And then find the value of Fy by gamma MO, 227.27. Now since this value is greater than the bending stress, then our batten columns are safe in bending stress. So let me just check quickly and point you out from where these formulas came. I haven't made a separate tab here, so I think I didn't save the tab here. Let me just see, and okay, just make sure that these stresses are lesser than these values that we have calculated here, Fy by root under 3 into partial safety factor for shear stress, and Fy by partial safety factor for bending stress. So this is both safe in shear and bending stress. So this is how you design for the batten columns. Now one final thing left is to design the connection between these batten columns and the built up and these channel sections, not built up, sorry. So in practical field or in reality, you see that most of these connections are made by welded connections. So if you are performing welding to connect these batten plates with your channel sections, then you have to check for the size and the length of the weld, whether that is sufficient or not. Instead, if you are using different bolts to connect these batten plates with the channel sections, then you have to design for that bolt group. We will look at the design of connections in a separate class. So this completes the design of batten columns in our today's lecture. And remember here that the size of these battens are coming out to be very large. Even the forces that is coming on our column is very much smaller compared to the force that we are designing for. So in these design lecture classes, what I'm telling you or what I'm discussing with you is only the design steps and the various codal provisions that you should refer to. One thing that I'm not dealing with in these design lectures, nor in today's lecture, nor in many of our previous lectures, is the optimization. It is your job to perform the optimization of the structure by performing various trial and errors. Just increase or decrease the section thickness or the length or any parameter in this Excel sheet, and then check for whether how greater optimization can you perform for the design of any element. So that optimization part I am leaving it to the viewers. In next lecture we will start with design of a new element, most probably base plate or connection. We will see what design we will be doing in our next lecture. I would like to end today's lecture here. So stay safe and thank you.